October 9th, 2002. Over the Bering Sea, cruising at 35,000 feet, Northwest Airlines Flight 85 is just past the halfway point on a trans-Pacific journey from Detroit to Tokyo. Outside, the air is still, quiet, deceptively calm. Inside the cockpit, it's business as usual, until suddenly the aircraft jerks left. Violently, the Boeing 747-400 enters a sharp, 40-degree bank with no warning and no input from the flight crew. The autopilot disconnects. Alarms begin to sound. Junior Captain Frank Gieb and First Officer Mike Fagan, just minutes into their flying shift, wrestle with the controls as the plane threatens to spiral. At 35,000 feet, over the freezing waters of the Bering Sea, something deep inside the aircraft has failed, catastrophically. The lower rudder has gone full left, and it's stuck. The 747 is fighting itself. Only brute force, asymmetric thrust, and decades of combined flying experience are keeping it level. There is no checklist for this, no procedure, and worse, they're in a communications dead zone. This is inside aero disasters. And this is the near-fatal rudder failure of Northwest Airlines Flight 85. Northwest Airlines Flight 85 departed Detroit Metropolitan Wayne County Airport at 2:30 p.m. Eastern Daylight Time. The aircraft, a Boeing 747-451, tail number N661US, the original prototype of the 747-400 series, now operating in commercial service. On board were 386 passengers and 18 crew members bound for Narita International Airport in Japan. The route was routine, over the North American continent, across the Bering Sea, and down toward the Japanese archipelago. 7 hours into the flight, at cruising altitude, flight level 350, the cockpit was under the control of Junior Captain Frank Gieb and First Officer Mike Fagan. Senior Captain John Hanson and Relief First Officer David Smith were on scheduled rest in the cabin. Conditions were stable. The aircraft was flying on autopilot with no reported weather disturbances. But that calm was abruptly shattered. At 5:40 p.m. Alaska Daylight Time, without warning, the aircraft rolled into a sharp left bank, estimated between 30 and 40 degrees. The autopilot disengaged immediately, and cockpit warnings sounded. Captain Gieb, initially suspecting an engine failure, disengaged remaining automation and attempted to stabilize the aircraft manually. But Flight 85 wasn't suffering a propulsion problem. It was a control surface anomaly, and a severe one. The aircraft's lower rudder, the larger of its two rudder surfaces on the vertical stabilizer, had gone full left with no command from the crew. This is known as a rudder hardover, a condition where the rudder deflects to its maximum limit and remains stuck there. To counter the left yaw, the flight crew applied full right upper rudder, opposite aileron, and later resorted to asymmetric engine thrust, increasing power on the right side to balance the aircraft. Flight 85 was now flying with its control surfaces actively fighting one another just to maintain straight and level flight. The situation was unprecedented and unaddressed by any checklist. Stabilizing the aircraft was only the beginning. Flight 85 was still over the Bering Sea, hours from its destination, and critically, in a communications dead zone. Standard radio contact with air traffic control was out of reach. The crew's initial attempts to declare an emergency failed. No ground station responded. Inside the cockpit, the rudder remained deflected left. The flight required continuous manual correction to avoid entering another uncommanded bank. Autopilot could not be re-engaged. The crew had no precise understanding of the failure's cause or scope, only its effect. A sustained, dangerous imbalance. Despite the absence of external communication, Captain Gieb and First Officer Fagan began preparing for a diversion. Senior Captain Hanson returned to the cockpit. With 4 qualified pilots now working together, the flight shifted to full manual coordination and resource management. The aircraft was turned toward Ted Stevens Anchorage International Airport, the nearest large airport with adequate emergency support and a long runway capable of accommodating a 747. Still unable to contact ATC, the crew used HF radio to reach another Northwest flight operating nearby, Flight 19. Using Flight 19 as a relay, the crew finally declared an emergency and coordinated their new flight plan. All onboard systems were monitored closely. Fuel remained stable. Structural integrity showed no abnormal signs. But the control issue persisted, and there was no guarantee the aircraft could be safely landed. Crew discussions with Northwest Airlines operations in Minneapolis confirmed what the pilots already knew. No existing emergency checklist accounted for this rudder configuration. The crew would have to improvise. Red emergency protocols were initiated. Flight attendants were briefed for a possible evacuation. Passengers were told of the diversion, but not the full extent of the threat. With Anchorage now in reach, the crew prepared for descent into uncertain territory. As Flight 85 approached Anchorage airspace, the aircraft was still compromised. The lower rudder remained fixed in full left deflection. Any deviation in manual input could trigger another destabilizing roll. The crew began configuring the aircraft for descent without the assistance of autopilot or auto-throttle. Every movement had to be deliberate. Trim, thrust, and aileron input were adjusted manually, constantly. Approach clearance was granted by Anchorage Center once radio contact was re-established. Runway 6R, one of the airport's longest, was selected. It offered ample length, minimal crosswind, and clear terrain approaches, a critical advantage for an unstable aircraft. Captain Hansen assumed control for the landing phase, with First Officer Fagan monitoring and adjusting control surfaces in real time. Junior Captain Gieb and Second Officer Smith handled systems and communication. Configuration posed challenges. Deploying flaps and gear altered aerodynamic balance, requiring immediate counter input. The rudder hardover reduced the aircraft's yaw stability, meaning even minor deviations in engine thrust or crosswind effects could push the 747 off course. To maintain directional control, asymmetric thrust was applied, higher on the right engines. This allowed the crew to maintain a near-straight trajectory despite the rudder's constant pull to the left. The approach was stabilized, but only by constant manual intervention. There was no margin for distraction, no room for error. Final descent was executed with surgical precision. Throttle inputs were fine-tuned down to seconds before touchdown. The landing gear was confirmed locked. The aircraft was aligned, but always seconds from instability. Flight 85 touched down safely on runway 6R at Anchorage. Emergency vehicles were standing by, but no evacuation was necessary. Against the odds, the crew had landed a compromised 747 manually, without injury to any of the 404 people on board. Once safely on the ground, Flight 85 was towed to a remote stand for inspection. Externally, the aircraft showed no signs of structural damage, but inside the vertical stabilizer, investigators would uncover a hidden failure with serious implications. The National Transportation Safety Board, NTSB, in cooperation with Boeing, began an immediate technical examination. The focus? The lower rudder power control module, a hydraulic unit responsible for actuating rudder movement via pilot input or yaw damping systems. Initial tests confirmed what the flight crew had experienced. The lower rudder was mechanically jammed in a full left position. Disassembly revealed the cause. A fatigue fracture had developed in the manifold housing of the power control module. Specifically, the metal casting that supported the yaw damper actuator had cracked, separating from the main unit and allowing uncontrolled hydraulic pressure to drive the rudder to its limit. This type of failure was rare, not a failure of moving parts, but of the housing structure itself. And critically, it was not externally visible. Standard maintenance procedures did not include inspections capable of detecting such internal fatigue. The rudder's split configuration, upper and lower surfaces, had ironically prevented disaster. While the lower rudder was locked left, the upper rudder remained functional. This, combined with right aileron and asymmetric engine thrust, gave the pilots just enough control to keep the aircraft stable. Without that redundancy, or without a full crew on duty, the outcome could have been far worse. The NTSB concluded that the probable cause was a fatigue fracture of the lower rudder power control module manifold, resulting in a lower rudder hardover. This was not a design flaw in the traditional sense. It was a material failure that had escaped all prior detection methods, and it prompted immediate regulatory action. Northwest Flight 85 never made headlines at the time. There was no crash, no injuries, no dramatic footage. But in aviation circles, the event became a turning point, an unambiguous warning that even robust systems can conceal silent failures. The aircraft, N661US, was not damaged and was returned to service after a thorough inspection. But the rudder control issue it revealed sparked immediate global concern. Boeing responded by issuing Alert Service Bulletin 747-27A 2397, urging operators of all 747-400 variants to conduct ultrasonic inspections of both upper and lower rudder power control modules, focusing on high-time airframes most susceptible to fatigue. The Federal Aviation Administration, FAA, followed with Airworthiness Directive 2003-23-01, making those inspections mandatory. It was later replaced by Directive 2006-18-17, incorporating broader safeguards and updated inspection intervals. This incident reshaped how structural fatigue was evaluated, especially in components previously believed immune to such failure. Traditional visual checks were no longer considered sufficient for certain hydraulic systems, but perhaps the most enduring legacy was human, not mechanical. The flight crew's response became a textbook case in cockpit resource management (CRM). With 4 pilots on duty, they coordinated seamlessly under extreme stress, delegating tasks, maintaining situational awareness, and making decisive calls without conflict or confusion. Senior Captain John Hanson later reflected, "This was a classic application of CRM. We weren't sure we were going to be able to keep the airplane on the runway." Their teamwork, communication, and technical handling earned formal recognition. In January 2004, the Airline Pilots Association awarded them the Superior Airmanship Award. Years later, the aircraft itself, N661US, was retired and placed on permanent display at the Delta Flight Museum in Atlanta. A survivor of the skies, a quiet monument to what almost happened, and to the people who stopped it. The near disaster of Northwest Airlines. Flight 85 wasn't caused by human error. It was prevented in spite of mechanical failure. A hidden fatigue fracture deep within the rudder control system set the stage for catastrophe. But it was quick thinking, disciplined flying, and flawless crew coordination that kept the aircraft in the sky. There were no checklists for what they faced, no standard procedures to fall back on. And yet, every pilot on board rose to the moment. Because in aviation, it's not only systems that keep you safe, it's the people trained to act when those systems fail. If you found this breakdown informative, make sure to like and subscribe for more real-world aviation investigations. And let us know in the comments, which case should we analyze next? Because sometimes disaster doesn't strike, it's narrowly avoided.